Hi, everybody, and welcome to our next lecture. This week, we're going to start Chapter 2 and cover sections 2.1, 2.2, and 2.3. As always, my goal is to introduce you to all the topics in the text, but I don't have time to cover every example, so you're always strongly encouraged to still read through these chapters in the text as well to see further examples, and then also use the My Math Lab video resources for additional videos on these sections as well if you find them helpful. So let's get started. First thing we're going to look at are increasing, decreasing, and constant errors of the function. And this part is directly related to the discussion that you have this week. So a function is increasing within an open interval if the y values go up from left to right. So basically part of your graph is going in this direction. So you have an upward trend. A function is decreasing within an open interval if the y values are going down from left to right. So for decreasing, it's going downward. And then a function is constant if your y values are staying the same within the open interval. So your constant graph will be perfectly flat, like a horizontal line, again, just for that part of the graph. So we're going to look at more complex examples here that are curves where some parts of the graph may be increasing, decreasing, or constant, whereas with a linear equation, right, or a linear function, it's always the same trend for the whole line. When we describe functions that are increasing, decreasing, or constant, we always use the x values, and we always use interval notation with parentheses. So this is the idea of an open interval. As a little side note, if you hear the words closed interval, those are with brackets. So increasing, decreasing, constant, we always use the x values there as the reference points. And then we always use open intervals, so parentheses there. And that's really important. That's a very common mistake. And the reason is because a single point can't be increasing or decreasing or constant. So that's why we don't include endpoints here. We use them as open intervals instead. All right, so I'm going to recreate a graph from your text. It's a pretty simple one, so we can recreate it pretty quickly here. And it looks like this. And it's not going to be to scale, so kind of just get the general shape here. All right, so some key points here. This point here is -1, -2. This point is 3, -2. This point is 5, +2. And those are the three main points that you need here. All right, so we're going to look at where this graph is increasing, decreasing, and constant. So let's start with increasing. And remember, we think about this in a left to right direction, right? So increasing means the graph is going upward as we look from left to right. And as I go from left to right, there's actually one point of the graph where that occurs, and that's from here to here. You have this kind of upward trend in the graph. Now, as we're looking at that, we always refer to the x values. So we're increasing from when x is 3 to x is 5. So we would write 3, 5. I'm going to do constant next, so that one's pretty obvious. So here you can, again, my graph is not perfectly drawn, but you can see that it's flat right there, and the y value does stay the same. So there's no change in the y value. So that is constant. And we're constant from -1 to +3. Now the last part here, and this is the more challenging one for this particular problem, I think, is decreasing. So the right part of the graph, I think, is pretty obvious, right? This is going downward here. So going from 5, and then it keeps decreasing forever. So you're going from 5 to infinity, right? For every other x value on the right there, it's going to keep decreasing. Now there is another part of the graph that's actually decreasing as well, and it's this part here. And the reason it's decreasing is because we read from left to right. So again, I know the arrow is telling you that it's going up forever, but if we read in the left-right direction, it's actually coming down, right? So you're reading in a downward direction. So that's where it gets a little bit tricky. You want to read always left to right. So we are coming downward here. and it stops going down at -1, and then it has the same trend for the whole left side of the graph, going off to negative infinity. So we're decreasing from negative infinity to -1, and then like we've done before, this is a 1 here, or -1. Like we've done before with interval notation, we can put that u in between our two intervals. All right, the next thing I want to talk about are max and mins. So a function has a relative maximum, also called a local maximum, if it has a maximum within a small interval. And it looks like typically a peak or the top of a hill. So here's an example, and I just have the citation here, or not a full citation, but the link to where I found the image. And this one actually has 3 relative maxima. Right here, right? There's a little peak right here and right here. So a relative maximum or a local maximum is a local maximum just in a small area. It doesn't have to be on the entire graph. So we do have 1, 2, 3 local or relative maxima. The A at the end is just the plural form of maximum. We also have 2 relative minima, or also local minima. These typically look like valleys on a graph, and we have 2. There's one here, and there's one here. So you see those little dips. And these are our local or relative minima. Now notice a few things here. The graph does keep going downward forever. So even though these are local or relative minima, they're not the absolute minimum, right? So there's a difference between absolute max and mins and relative. Your book doesn't stress absolute max and mins that much, so we're not going to worry about that here. But I just want to point that out, that a relative max or min does not have to be the highest or lowest overall. So graphs can have 0, 1, or multiple relative max and mins. This one here, there is no absolute min, right, because it does keep going down forever. And then actually this point would be the absolute max, that is the highest overall. So that's a different concept than what we're talking about here. So the wording can be a little bit tricky here. We can say, so I'm just going to pick on this point here right in the middle. So this is the point 0, 3. So we could say things like there is a relative maximum at x equals 0. Or I could also say something like the maximum value for this point, value is 3. And when we talk about y value, the value that we're referring to the y value. So this is where it gets a little bit tricky. As you're answering the homework questions, you want to read really carefully. If they're talking about more of a location question, they usually want the x value. If they're talking about what is the maximum value here, they're usually referring to the y value. So you want to look at the language really carefully, and it does get tricky and confusing, so it may take a little bit of practice there. But again, if they're referring to more like a location, you see the word at, then it's probably the x value, whereas if they use the word value, then it's probably the y value. So it does get a little tricky. But so just pay attention to that on the homework and try to see those differences. All right, so for the next example, I'm going to use my graphing calculator here to graph this problem. And again, you can use any graphing calculator you like. My favorite happens to be Desmos because it's free and it's pretty easy to use compared to some of the other ones. And we're going to look at the intervals on which the function is increasing or decreasing, and also figure out the relative max and mins there as well. So you can go ahead and do this on your computer, or there is an app as well that you can use. So I'll just kind of show it on the screen here. So here I have the Desmos app on my phone. I don't know if it'll show well. Let's see. That looks better. Just kind of lower that brightness a little bit. All right, so what I can do here is I can type in my function that's given, and I'm just going to type it in like it reads here. If you want to use f of x, you can. If you have trouble typing that, you can also just use y there. So I can type y equals, and then I'm going to do 0.1 x, and then I'm going to use the a to the b here to put in a cube, and then minus 0.6 x squared, and then minus 0.1 x plus 2. So I'm just typing in the here, and then again, if you have the it on your laptop or your computer instead, it works very similarly. It's actually probably a little bit easier to use because the keyboard is bigger, but you can see the general shape here. And the nice thing is that you can just tap along and also see some of those key points here. Again, we don't have to show all of them at the same time. But Desmos is very nice where you can tap or either click on the graph and also find those key points. So first of all, I do see a relative max and a relative min. Notice that this graph does keep going down forever and up forever. So these are not absolute max and mins, they're just relative, meaning that they're in a small area, they are the max and min value. So my max value is right here, and you can see that it's not quite at 0.2, although it's very close to it. It does say to approximate, so you could maybe round that to 0.2 if you wanted to here, or you could use 1 or 2 decimal places. So we could say that there is a relative max at x is about negative 0.08, for instance. Or again, if you want to round more, you could just say at about 0, right? That would still be accurate if we're approximating. And the max value is about 2.004. So if I round that to 2 decimal places, it's about 2. For the min, that would be down here, right? See, we see a little valley there. And if I click that point again, it's about at 4, negative 1.6. So our relative min is at x is about 4 or 4.08 if you want to go out a few more decimal places. And the min value is about negative 1.60 if I round to 2 decimal places. So we have our relative max and min. Now, if I look at the graph, I do see that it is increasing here to here, right, coming in, and then it increases again from here to here. In the middle, I do see this downward piece, so I have a decreasing piece right in the middle there. Remember, we read left to right, so we're increasing here, then we switch to decreasing, and then back up to increasing. So looking at my intervals, we're increasing from here all the way to this relative max. So at about 0 or negative 0.08 if we're going to be a little bit more accurate there. And it's increasing on the left, right? It doesn't ever change. So it's going to go from negative infinity to negative 0.08. And then it's going to continue increasing again from this point upward. So 4.08 to positive infinity. Remember, we use our x values when talking about increasing or decreasing. Again, if you were rounding a little bit more, you could say, negative infinity to 0 and then 4 to infinity. So again, depending on how much we need to round in the question. For decreasing, just in between here, so going from x is negative 0.08 to 4.08. Or again, if you're rounding a little bit more, from about 0 to 4 is where we're decreasing. And it is not constant anywhere, right? It's never flat, so that piece does not occur. All right, let's look at an application here. So let's say a community college, this should say has 30 feet of dividers with which to set off a rectangular area for our student testing center. If a corner of the math lab is used for the testing center, the partition needs only to form two sides of a rectangle. So first, let's actually think about what's happening here. So we have a math lab, right? So let's say it's a room. Well, it looks like this, right? So here's our math lab on campus. And we're looking for, again, a rectangular area for the testing center. And we're going to do it in the corner of the math lab. So I would like to maybe put the testing center like here. Well, if I put it in the corner, the nice thing is that I can use the walls of the room that are already constructed, right? So I don't need to create new walls there. I just really need to create two walls. I need to create this wall, and I need to create this wall. So that's where that partition piece is coming in. So we have 30 feet of these partitions or dividers. If you kind of think about maybe like cubicles and things like that, that's sort of what my brain is going to here, like these little dividers to section off part of the math lab. Express the floor area of the testing center as a function of the length of the partition. So let's look at this here, right? So here's our testing center. It is rectangular, so we know area is going to be length times width. So maybe this is our length and this is our width. I know nothing about the two sides, so I am going to define things a little bit here. So let's call the length x. Well, how can we represent the width? And the way we can do that is we can use the idea of the total. This is a trick that we've seen before where there's not really much information, but I do know the total. So my width is going to be the 30 feet of dividers minus whatever the length is, right? If my length was 10 feet, then my width would be 30 minus 10 is 20. That would use all my dividers and allow me to create that rectangle. So the area, again, is length times width. So I can write it as a function using a of x, a for area and x because that's our variable. Our length is x and our width is 30 minus x. And I can distribute that as well and just kind of clean this up. So 30x minus x squared, or if you want to rearrange the order, that's okay too. Oops. Let's find the domain of the function. So domain are your x values, right? Now this here, you actually have to think a little bit. Right? If I look at this function here, it is a quadratic, and there are no main issues that we've seen, right? So if I think about this, there's no dividing by 0. There's no square root where I could get a negative number, like an imaginary number. I don't see any of that. So your inclination may be that, well, the domain is all real numbers, right? There's no issues. Now that would typically be true, except for the fact that I do have restrictions here because it's a real world problem, right? So again, our initial thinking is like, oh, well, the domain is everything because, again, there's no division by 0, there's no issues. But that's actually not true here because I do have restrictions. They're just sort of hidden. And the restriction is that I only have 30 feet of dividers. So if my length or my x is my length here, well, I can have it be at most 30, right? I don't have 60 feet. I don't have 50 feet. I can't have x be more than 30. All I have is 30 feet. Also, I can't have x be negative, right? It doesn't make sense to have negative length. So I am dealing with values between 0 and 30 here. Now the other thing is I actually do not want to include the n values here. The reason is that if the length was 0, then I would only have one wall. I wouldn't end up creating two walls, right? Or if my length was 30, again, I would not have any material for a second wall. So our domain has to be strictly between 0 and 30. So not equal to, but strictly, greater than 0, but less than 30, and that would create two walls, not just one. This is another one that would be great to graph on Desmos. So, if I just go to my Desmos graph again here, I can go ahead, X that one out and put in a new one. Again, I don't need to use the function notation if I don't want to. I'm just going to use y equals, and I'm going to type in 30x minus x squared. And I'm going to zoom out here a lot because I can't really see my whole graph. So I have to zoom out quite a bit here to actually see what this looks like. And just kind of see if I can get a decent picture there. So we can see that's what it looks like. I'm just going to kind of quickly draw it. Now, our domain was from 0 to 30. So I don't really need to have a large portion of the negatives here, right? And I can see that we do cross right there at 0, 0. And then we hit here again at 30. So my graph is this U-shaped piece. And again, it does keep going, right? So it does keep extending, but I really don't need those parts that extend down because my domain is only from 0 to 30. So I'm really just looking at the top part of the graph here, and I don't really need those other pieces. The other thing that may be nice to know is to figure out what this relative max is. So that's at 15 to 25. And again, this is at 30, this is at 0. Our last piece here is we want to find the domain that maximizes the floor area. Now, that word maximize, hopefully that's a good hint for you. And we're looking at the area. So I want the area to be as big as possible. Now, remember, our area here was our y. So our y-axis is actually the area. So if I look here, my maximum occurs when the area is 225. So you want to be careful. This is your x and this is your y. This is not your length and your width here. Your x is here. That is your length. That's how we defined it. But the 225 is not the width. It's the area because that's the function that you're graphing. So the length is 15 feet. And then the width, then, using our formula of 30 minus x, would be 30 minus 15, which is 15 feet as well. So actually creating a square ends up being the best option. And that does give us a maximum area of 225. And don't forget, this is square feet or feet squared. So here we're using that graph to help us find our relative maximum. And we just want to be careful with how we've defined everything, right? So y here again is not the width. It represents the area in this case. All right, I want to look at piecewise functions next. Piecewise function just means that a function is defined basically in pieces or parts for different parts of the domain. So here's an example. You can see there's 3 different parts, and each one is relative for a different part of the domain. So the first one is used when x is less than -2. The second one is used when x is between -2 and 3. And then the third one is used when x is greater than 3. It's still one function, but again, it's called piecewise because it has different parts to it. All right, so let's start here and find these values. So don't forget, in this notation, the value inside the parentheses is your x value. So what you want to do is figure out where your x value lies. So notice that it would be in the first group here for x equals -5 because -5 is less than -2, right? It doesn't fit here, it doesn't fit here. It's only going to fit in one of the rows. So it fits in the first row, so I use the first expression. So I'm going to go ahead and use that x plus 1 and plug in -5 plus 1, which is -4. So f of -5 is equal to -4. For our second one, again, don't forget that is your x value. So your x value is -3. You're not plugging into everything. You're just using the one that makes sense. -3 is also less than -2. So it also fits in the first row. So I'm only using the first row here. So it would be x is -3 plus 1 is -2. For the next one, I have 0. I'm using different colors to kind of show you what's going to happen. So our x value here is 0. So 0 is not less than -2. 0 is in between -2 and 3, right? It fits in here. So this one fits here, so I'm using this expression for my answer. So f of 0 is just 5. For f of 3, you're going to notice the same thing. Again, my x value here is 3. Well, where does that fit? You want to be a little careful here. In the second expression, we are including the 3, whereas in the third one, it's strictly greater than. So 3 fits here. So again, I'm using this expression. For the last two, you notice that your x's are getting bigger here, right? Our x is 4. So where does it fit? Well, 4 is definitely bigger than 3. So it fits in this row. So I use this expression. And it's going to be 4 squared. 4 times 4 is 16. You want to be careful when you plug in with a square. The whole thing is being squared. I don't have any negatives here, so it's not an issue. But if you were plugging in a negative, make sure you square that negative as well in an example like this. And then for the last one, you have x is 10. Again, 10 is also greater than 3. So I would use the square piece. So I'm doing 10 squared, which is 100. Now, all of these can also be converted to points as well. So if you wanted to graph this, I'll do a graphing one next, but if you wanted to graph this, you would really graph it in parts. So it's going to be one picture in the end, but for values less than -2, your graph is going to look like an x plus 1 function. For values between -2 and 3, it's going to look like just a constant 5. And then for values greater than 3, it's going to have the shape of an x squared function. So even the graph kind of looks like it's in parts as well and pieces, even though it's all the same graph. So let's do a graphing one here. So you have a function. This one has 2 parts. So it's defined as the first piece for any value as long as it's not -2. And then for this, when it is -2, we use the value of 3. The reason that works is because if you plug in -2 to the denominator here, you do get an undefined value. So we can't use that first expression there. One thing I do want to note is if you can simplify things, you would want to do that. So x squared plus or minus 4 factors into x plus 2, x minus 2. So I actually can simplify this a bit and write the first part as a simpler expression as x minus 2 instead. So can just kind of simplify that a little bit just to make it easier to work with. So what you do for graphing is you're going to set up your table still, and you're just going to do it in pieces. So I'm going to do this part first, this expression first, and I'm going to plug in a whole bunch of different values except for -2. So maybe I plug in -3. So I get -3 minus 2 is -5. Maybe I plug in -1. So -1, -3. Maybe I plug in 0. So I get 0 minus 2 is -2. Maybe I plug in, I don't know, +2. So 2 minus 2 is 0, and so on. I can plug in as many points as I need to kind of see that pattern there. So let me start with that piece. I'm just going to go by ones there. So what I have here, so my first point is at -3, -5. 1, 2, 3, -5, so about right there. -1, -3. 0, -2. 2, 1, 2, 0. And I can see that this is a linear function, so I'm getting this nice linear graph. Now, just be careful here, because at -2, the value is going to be 3. -2, 1, 2, 3. So that value is actually up here. What I like to do, and this is what I suggest when you're trying to graph piecewise functions, is I would also graph, if you can, the value at that endpoint. So here, we're not supposed to plug in -2, but I'd like to know what would happen. So when I plug in -2, I would have -4. So this point here is a hole on the graph. It's not on the graph, right? We can't be doing this, but it helps visually to see what's happening there. So at -2, -4, I should have a hole here on the graph. So what's happening is the rest of this is all linear, right? If I'm not sure, I can find some more points, but there's a hole there and the point is really up there. This is called that it's discontinuous, by the way. When there's a hole, so if there's a hole or a split or a jump, you have to pick up your pencil. It's something that's discontinuous. Another example could be if your graph kind of looks like this. It's like if you have a split in your graph in two parts. So a lot of times, not always, our piecewise functions may have holes in them. Sometimes they don't, but they can. So it's just something to kind of watch out for. But I do recommend looking at endpoints, right, to see where that pattern ends and what would happen there. So again, that point -2, this is not on the graph, but I know where the hole is, so it helps me to draw the graph more accurately and know that the hole is here, this is a line, and then the other point goes up top. So I do recommend that, again, just to help you visually see what's going on with these examples. On the next page, we have an example of kind of another, it's sort of a piecewise function, though the graph is very piecey, although this is defined as one thing. And this is an example of a step function. And because the graph actually does look like a series of steps. Okay. So what the greatest integer function is, so this is the notation we sometimes use for like a double bracket, is it spits out the greatest integer that is less than or equal to whatever you plug in. So for instance, let's do f of 3.5. So I'd ask myself, okay, what is the greatest integer that's less than 3.5? Well, the answer is 3. What if I plug in 5.1? What is the greatest integer that is less than 5.1? It's 5. So it's the integer right below it. If I do 10.9, the greatest integer below this is still 10, right? It's not 11. It's always going to be down. The only time that it is not down is when the number you plug in is an integer and the answer is the same, because it is less than or equal to. So 4 is the closest integer, either the same or below to 4 here. Let me show you a couple more. Let's do a pattern. So we know f of 4 equals 4. If I plug in f of 4.1, the greatest integer less than 4.1 is also 4. If I do 4.3, the greatest integer less than 4.3 is also 4. If I do 4.7, the greatest integer less than 4.7 is also 4. If I do 4.999, the greatest integer less than this is still 4. You don't bump up to 5 until you actually plug in 5. So what happens is you see this really interesting graph, and it looks like this. So let me show you. So let this be 1. I'm going to count by halves here. So what's happening is from 4 to 5, right? Did I count right here? Okay. So from 4 to 5, your answer is always 4, right? So up here at 4, it's 4. And then it's the same thing all the way across until I get to 5. When I get to 5, it does bump up to 5. And then it would keep going. Like if I plug in 5.1, I still get 5 and so on. So what happens is you have a closed circle at the lower integer, and then you put an open circle at the upper integer where it jumps up. And that pattern continues. And if you plugged in more values, you would see the same pattern. So at 3, it's 3, and it goes all the way. But once we hit 4, it jumps up. And at 2, it's 2. And again, it goes over, and then you have this open circle. So you basically are creating these steps, which is why it's called a step function. And so on. So if you plug in more values, you'll see this pattern the whole way down. So this is a pretty famous, probably the most famous step function called the greatest integer function. It is a function, though. It does pass the vertical line test because, when you go through a line here, because there's an open circle on one of them, that circle doesn't count. So there's a hole there. So you only have 1 point at each vertical line. So it is still a function. All right, the next thing I want to talk about is the algebra of functions. So how can we add, subtract, multiply, and divide functions? And it's actually pretty straightforward. It can be tedious because functions can be pretty complicated, but to add functions, you literally just add them together. To subtract them, you just subtract. To multiply, you multiply, so you would distribute or FOIL, etc. And then to divide, if you can, you would divide and try to simplify like we did with rational expressions. What happens with a domain is basically, let's say f and g are functions and x is in the domain of each function, then they can be added, multiplied, or divided together, and the domain is going to continue. So you look at the original functions, you find their domain, and then you basically just put them together for f plus g, f minus g, and f times g. The only thing is when we have division, you always create an extra issue, and you do need to make sure you're not having a denominator of 0. So when you're looking for the domain there, you will have extra values that you will probably have to exclude to make sure your domain is not 0. All right, so let's look at some examples on the next page. All right, so here is my starting functions. So I have a linear function and I also have a radical here. And I'm going to work with addition in this case. So this first notation here, f plus g of x. Everybody gets confused. They start multiplying things by x. Remember, this is function notation. We're not multiplying by x here. This just means to take the f function and add it with the g function. So you're literally just adding them together. So my f function here is x plus 1. My g function is root x plus 3. If I could simplify, I would. This one I can't really even do anything with because I have that root there. So it's just x plus 1 plus root x plus 3. And that's it. Again, if I had like terms, I would add them, but I don't. Now for b, you have f plus g of 6. So they're basically saying, well, take your function, your f plus g function, which is this one, and plug in 6. So you're going to just take each x and replace it with 6. Just like we have been before. So here 6 plus 1 is 7, 6 plus 3 is 9, the square root of 9 is 3, and I get 10 for an answer. So f plus g of 6 is equal to 10. So once you have the function, you're just plugging it in. I do want to make a note here is that this is actually the same as doing them separately. So if you did f of 6 and then plus g of 6, you would get the same answer, right? So if I look at f of 6 here, I would do just 6 plus 1, which is 7. G of 6 is root 6 plus 3, so root 9, which is 3. And then if you add them together at the end, you get the same 10. So this is a really nice tip because sometimes it may be easier to add them individually or to find the values individually first based on the information you have. So you can do it either way. You can find them individually and then add, or you could find the function first and plug in. And this is also true for subtraction, multiplication, and division. So you can do it either way. Now for C, we're looking at f plus g of negative 4. So I'm going to do it this way here. So I'm going to plug in. So I have negative 4 plus 1 plus negative 4 plus 3. So I have negative 3 plus the square root of negative 1. Now, this is not real, right? This is not a real number. This is imaginary. So what's happening here is I'm not getting a real answer. So negative 4 is not in the domain, right? So this is not a real number. This one doesn't work. So let's take a step back here and actually look at the domains for a second. So for this first one, it's linear, right? So I don't have any issues here. There's no division by 0. There's no roots. The domain of that function is all real numbers. This one, though, I do have an issue, right? I do need to make sure the inside of the root is not negative. So if I solve this and I subtract 3 from both sides, I do see that x has to be negative 3 or bigger. So that's why that negative 4 is not working. It's because of the g function. So putting this all together, to find the domain of f plus g of x, you just combine the two things. So here, I know this is all real numbers, but this one does have issues. So putting this together, you have to go with this one, right? Because it's not going to work if anything is less than negative 3. I'm not going to be able to add those things. So your domain here is negative 3 to infinity. So when you have more than one function that you're trying to kind of combine, you combine your domains. So you find the values that work in both of them, and that's your overall domain here. Or x is greater than or equal to negative 3. All right, let's do another one. So here I have two different functions. I have a parabola or a quadratic here, a curve, and then I have a linear. So we're going to start by finding the domain. So I'm going to find them separately first. So I have f of x, and the domain there is all real numbers, right? There's no division by 0. There's no root. It's not an application, so it's just a regular equation. So my domain there is all real numbers. And if I look at g of x, my domain there is also all real numbers, right? It's just linear. There's no issues. So putting these together then, for f plus g, for f minus g, and for f times g, these all have the domain of all real numbers, right? Because I'm just combining them together. The only issue I have to watch out for is the division one, because when I do f over g, what happens is I have x squared minus 4 over x plus 2. So I've created a denominator. I do need to make sure my denominator is not equal to 0. So I need to make sure that x plus 2 is not equal to 0, or x is not equal to negative 2. So the division one, that one domain is different. Everything else is fine, but when I divide, I create an extra problem. So I do need to make sure that I get rid of that negative 2. So x cannot be negative 2 here for the division one. So you are just combining them together, but again, watch out for this one because you could create extra issues like we did here. Now, as a little side note here, this one actually does simplify further. So if you are dividing, you would want to actually simplify this further, which you could do. But the domain still stays the same. You always start with the original before you find the domain. Let's look at B. So B asks us to find f times g of x. So I take my f function, and I take my g function, and I just multiply them together. I don't multiply by the extra x here. That's just notation. So I'm just multiplying those functions together, and I'm going to distribute. So x squared times x is x cubed. X squared times 2 is 2x squared. On the inside, I have negative 4x. And then here, negative 4 times 2 is negative 8. And of course, if I could simplify this, I would, but there's nothing I can combine. So this would be my final answer. If I'm doing subtraction, again, you're just subtracting the functions, but you do want to be careful with that minus sign. So my f function is x squared minus 4 minus my g function is x plus 2. So don't forget, when you are subtracting, you are distributing that negative, and that's the mistake that most people make. So I have x squared minus 4 minus x minus 2. So I have x squared minus x, and then combining my like terms, I have a minus 6 here. So again, we're just being a little bit more careful as we go through, and you know, watching out for things like distribution and so on there. Okay. So the difference of two quotients is another way that we can combine and work with functions. So in section 3, we learned about slope, which is also called an average rate of change. So here's a nonlinear function. They're looking at the curve here, the blue curve, not the red. And we actually can find the average rate of change of curves as well, which is pretty interesting. So here you have a point here. And there is an error. This should be x plus h, by the way, comma. And then there's another point here. So you just have 2 points that are a little bit away from each other. So usually the h is a small value. Just as a little example, right? Maybe one of your points is, you know, 3, 5, and the second point is like 3.2, and then I don't know, maybe this is 6 or something. So that change between the x's is usually pretty small when we're finding average rate of change, although it doesn't have to be. So that's really what we're looking at here, is usually 2 points that are kind of close together. And finding the average rate of change is just finding the slope between them. So let's say, you know, your first point is, you know, x f of x, and then your second point is x plus some value h. That's, you know, a little bit further away. And what happens here is the difference quotient is the slope of this line, which is just a line between those 2 points. So you're technically finding the slope of the line that connects the 2 points that you're looking at. It actually is the same formula as y2 minus y1 over x2 minus x1. It's just that you're using function notation. So notice here, my y is f of x plus h, and my other y is f of x. And then our x values are x plus h and x. Now when you subtract here, those x's are going to cancel in the bottom, and you are left with this as your final result. And this right here is what we call the difference quotient. Now, for now, there's not really much that we're going to do with it. We're going to work with it next. I'll show you an example and how to simplify it. But this is really a calculus piece here, which is, I think, really interesting. Basically, what happens is, as you let that h value go to 0, so you let those 2 points become closer and closer and closer, you actually can find the average rate of change of a single point, because you put those 2 points closer and closer and closer together, you know, infinitely many times, like so close, that you can almost find the rate of change at an exact point. And by letting h go to 0, we can do that. This is the beginning of calculus, and how we find, how we do differentiation as well. So just a little tip there that we'll do a little bit of work with it here, but if you're going on to calculus, this is a super important function. All right, so here's the function we're going to work with, and we're going to use the difference quotient here. So I'm going to just write that up top so we have it. So that's the difference quotient. So I'm going to plug everything in there. Now, I like to do this in parts. So the hardest thing to find is the f of x plus h. What you do is you take your f function and just replace your x's with x plus h. So this becomes 2x plus h squared minus x plus h minus 3. So I'm replacing all the x's in my function with x plus h. This one's a little bit of a tough one, because you have that square. So you do have some multiplying out that you need to do here. And we're going to go ahead and distribute. And I'm just going to do two at a time. So I'm going to start with the 2 first. So I have 2x plus 2h. I'm going to distribute this negative as well, just so I don't forget to later. And then I'm going to FOIL this leading piece as well. So I have 2x squared, 2xh. On the inside, I have another 2xh. The order of the variables doesn't matter here. And then plus 2h squared. And bringing down the rest. And I'm going to do a little bit of simplifying. So I have a 2x squared. These guys can go together to give me 4xh. And then everything else I'm just going to rewrite. So now I like to simplify in. So this whole part is this. So I'm going to plug that in. It's going to be 2x squared plus 4xh plus 2h squared minus x minus h minus 3. I'm going to subtract that with the original function, which is this one. And then that whole thing is going to be over h. And I'm just going to take my time here and start simplifying. So I'm going to distribute through, and I get 2x squared plus 4xh plus 2h squared minus x minus h minus 3 minus 2x squared plus x plus 3. So making sure to switch all those signs over. And you should see that a lot of stuff typically cancels out. So for instance, negative 3 and positive 3 cancels, negative x and positive x cancels, 2x squared and negative 2x squared cancels, and what I have left is 4xh plus 2h squared minus h all over h. Now I can actually factor in h out of the numerator because they all have one. And when I do that, I'm going to notice that my h's here are going to cancel. So I'm left finally with 4x plus 2h minus 1. And that would be the answer to the difference quotient. Now again, why is this helpful? So what you'll see in calculus is that what we basically do is we let the h value go to 0. And when h goes to 0, you're left with just 4x minus 1. And that expression will actually give us the slope or rate of change for any x value on that function. So I could plug in, x is 2 and see what the slope would be at 2. So we don't have to worry about that here, but it's a really great application here that you will see if you continue on. All right, the last thing we're going to talk about today is composition of functions. This is another way we can manipulate functions. And you actually put one function inside of another. Now, you're actually used to plugging things in, right? Like if my function was x plus 2, and I said, okay, can you find f of 3? Hopefully you guys would know by now that I would just plug in 3, right? And I get my answer. So we're evaluating, right? We're plugging in. We're going to do the same thing here, but instead of plugging in a number, we're going to plug in a function. The notation for composition is an open circle, or you can also write it with parentheses. These mean the same thing. The way we read it is f of g of x. So you use the word of there to read this. And order does matter here. So in this case, the outside function is f, and the inside function is g. So order is important. You can see that the inside function comes second in the notation, and that's the one that goes into the outside function. So let me show you an example, and hopefully this will make a little bit more sense here. So I have two functions. I have my f and I have my g, and I'm going to go through some compositions here. So for a, we have f of g of x. Again, that of x does not multiply anything. It's just notation. F comes first, so this is my outside function, and g comes second, so this is my inside function. The outside function is where you start. So my starting function here is the f1, so I'm just going to rewrite it, 2x minus 5. And what you do is you take your g function and you plug it in to the x. So what ends up happening here is you have 2, and then my g function is x squared minus 3x plus 8. So we're using the outside function as the lead function here, and then you're literally plugging in the other function for the x. And now you would simplify. 2x squared minus 6x plus 16 minus 5. So we have 2x squared minus 6x plus 11. For B, notice the change in order, and that matters. So this is our outside function now. F is our inside function. So again, we start with the outside function. So I like to just rewrite it. X squared minus 3x plus 8. So what we're doing here is we're going to take those x's and we're going to replace them with whatever the f function is. So here's my f function. So I have 2x minus 5 is going to get squared minus 3, and then again it's 2x minus 5, and then plus 8. And then we're going to have to do that work out. So here, 2x minus 5 times 2x minus 5. And then I'm going to go ahead and have to multiply. So I'm going to save some time and just give you the final answer for here. And what you get here should be 4x squared minus 20x plus 25. Again, I'm saving some work, so you'd have a minus 10 and a minus 10x to get the 20 in the middle. Here you would distribute, get minus 6x plus 15 plus 8. And after you combine like terms, we have 4x squared minus 26x, and then 25, 15, and 8 will give us 48. You can plug a function into itself. So here you have f of f. So your outside function is f and your inside function is f. Again, start with the outside function. So it is 2x minus 5. And then you're going to replace the x with whatever the inside function is. So we get 2. And then because it's f again, we write another 2x minus 5 minus 5. This is a topic that is very new for students usually, and it does take some getting used to. I really think it helps to use color here, and again, to take your time. So I like to write my starting function first. I like to circle my x so I know what I'm replacing, and then I go to the next step. So I find that helpful here. Now the last one, you have a number instead. So what you're going to do is take your f of g function, which was this one, right? And we're just going to go ahead and replace it with 7. So once you have a function done, you can take it and replace the answer with the number just like you normally would. So 7 squared is 49. Let's see, 49 times 2 is 98. Here I have 42 plus 11, and I get 67. So you're able to use those functions once you have them, and go ahead and plug in numbers as well. Now, a little note here, which again, sometimes there's more than one way to do something here. Another way to do f of g of 7, let's say you don't have the function already done, and you don't really want to do it. Well, what you can do is you can find it here, but do one step at a time. So you would do g of 7 first. So I would do 7 squared minus 3 times 7 plus 8. So 49 minus 21 plus 8, which is 36. And then this becomes f of, now this became 36. So now you do the f function second. So we would have 2 times 36 minus 5. Which is 72 minus 5, which is also 67. So that's another way that you can do it. And again, this is helpful, particularly if you don't have the starting function already done. You just work, inside to outside. So you do the g first in this case, and then once you have that answer, you plug it in to the f. And that's another way that you can do composition when you have numbers. Now, the domain is actually a little bit tricky. So first, let's go ahead and compose, and then I'm going to show you how to find the domain of a composite function. All right, so my outside function is the f, my inside function is the g. So again, I'm going to start with my outside function. which is this one right here. So square root of x. And then what I'm going to do is I'm replacing the x with the g, right? So I'm just going to go ahead and plug that in. So I have that square root, and then the g is just x minus 3. Now there's nothing to really do there, right? If I could simplify, I would, but there's not. So this composition is pretty quick, and I can go ahead and just plug that right in. Now, how do you find the domain? And there's different ways to do this. So you may read it differently elsewhere, but this is my favorite way to do it, is first find the domain of the inside function. So in this example, our inside function is g of x, which is x minus 3. There are no domain issues there, right? There's no division by 0, there's no roots, so there's no issue. Domain is all real numbers. Then you find the domain of the actual composite function that you just found. So that would be this one here. So if I look at f of g of x, well, I do have a root here, so I do have to be careful. I need to make sure the inside of the root is not negative. And when I add 3 to both sides, I do see that I have to have the x is at least 3. And then what you do is you put it together. So you combine both of these and basically just make sure if there are any issues, you exclude issues in both parts. So there are no issues here, there are here. So I need to make sure both of these work. So I need to exclude these values here. So my final domain is that I have to have all values that are greater than or equal to 3. So you put both of these together. If I had issues up here, you know, like let's say, I don't know, x could not be 4 or something, then I'd have to also include that in my domain here. So I need to make sure that the values work for both pieces. And that's what you can do. This first piece is actually really important. It doesn't often have any issues, but when it does, they're easy to miss because you don't always see them, right? So I can see the final function. I'm used to looking at that, but a lot of students forget to check the inside function, and that is really important when finding domain as well. The last piece here is that composition goes both ways, so we can actually decompose and break something back down. So here's a final function, and they want us to break it back down. They want f to be the outside function and g to be the inside function. And usually they should be pretty obvious. So notice here how 2x minus 3 is actually inside something, right? This is clearly inside that 5. It's inside parentheses. So the inside function then should be 2x minus 3. And then the outside function, in this case, well, what's happening here? It's being raised to the 5th power. So your outside function is x to the 5th. And again, you can always check this, right? If I do out f of g of x, right, x to the 5th is my starting function. I plug in the g, and I do get what I started with. So we can go both directions and decompose as well. Sometimes there is more than one answer with decomposition, but usually for my math lab, they want the most obvious one. So typically the thing that's inside will be in parentheses, in a denominator, in a root. So it's usually going to be very obvious that one of them is inside something else. We covered a lot today, and particularly the composition I know is usually a tougher topic for students. So really take your time there. I do recommend using color to help keep things straight. And of course, if you have questions, don't forget you can always send me a message. Or if you need help finding additional videos or resources, again, feel free to reach out. And I'll see you guys next time.